Hey everyone, welcome back, and we are on to question 20 in the 2019 B test. The question reads, a block on a ramp is given an initial velocity v0 upward along the ramp. It slides upward for a time tu, traveling some distance, and then slides downward for a time td until it returns to its original position. What is td in terms of tu? The height of the incline is 0.5. 0.6 times its length, and the coefficient of kinetic friction between the block and the incline is 0.5. So the premise of this question is basically the force. You can imagine that the force diagram going upwards along the ramp is just going to be like this. So basically the force of gravity is pulling it, giving it a negative acceleration, and the force of friction is also giving it a negative acceleration, because friction always opposes the direction of motion, right? And then while it's going down the ramp, it's gonna have the same gravity component of gravity pulling it down, but in this time the friction is going to be pointing in the opposite direction. So acceleration is going to be a lot less for when it's going down. So basically, the question comes down to, you have these two kinematic equations. Delta x is equal to 1/2 a1. I'll call it a1, but because it's the acceleration that it takes for you to go up the ramp, so a1 is going up the ramp. Actually, I'll just call it au for going up the ramp, times tu squared plus v0 times tu. And delta x is equal to 1/2. Sorry, this is negative 1/2 a, right? Because it's going to be in the opposite direction of v0. And then we also have delta x is equal to 1/2 a down the ramp, t down squared. Yeah, because it doesn't start with the initial velocity. And these two delta x's are going to be the same because we want to see it going back down to the original position, so delta x will be the same. We can figure out the accelerations, and then we can plug the accelerations in and simplify it down that way. But there comes an issue with this v0. We don't really know what this v0 is. Before we go any further, though, what we can do is we can actually reverse this equation. And what I mean by that is pretend that it's already, so the block is going up the ramp. Now let's pretend that it's already up the ramp and it's going down the ramp, but the acceleration is not acceleration going down, rather it's acceleration going up. And the reason we can do this is the same reason why we can, like, instead of so like say you wanted to find, the time it takes for something to reach its maximum height, right? You throw a ball straight up and you want to see the time it takes for it to reach the maximum height. The equation for it going up, throwing it up, is like delta x is equal to negative 1/2 a t squared plus v0 t, right? We need to know this v0, but we also can just consider if it was already at the top of its trajectory and it was going downwards, right? Delta x is equal to 1/2 a t squared, and this way we don't have to consider v0, and it also describes the motion of the ball, right? This is something called time reversal symmetry, and it applies for all the kinematic equations. So we can actually, along the same line of reasoning, we can say that this delta x is equal to 1/2 a down t up. Sorry, this is also a up t up squared, right? We just won't consider v0. And now this is a lot easier. We can just set them equal to each other, and then we have a u tu squared is equal to a d t d squared. So let's figure out exactly what au and ad are. So this is going up and this is going down, and we know that the acceleration, well, we know that this is the force of friction, this is the normal force, this is force of gravity. So let's see what we're given. So Fg is obviously just mg, and this angle here, theta, it's going to be this theta right here as well, and this theta, actually this is a 6, 8, 10 triangle, so we know this is 0.8 times L. We don't know exactly what the angle is, but we don't need to care about exactly what the angle is either, because we're just looking at the sine and cosine, which we can just look at similar triangle here, right? So let's see what the force of friction is. So the let's see, the FG y component is equal to mg times cosine of theta, and cosine theta we can see from this similar triangle is 0.8 L over L, so 0.8 times mg, right? And that means that normal force is also equal to 0.8 mg. And we also are given the coefficient of kinetic friction between the block and the incline 0.5. So for the force of friction is equal to this thing times 0.5, which is 0.4 mg, right? So let's look at the, let me just enclose this guy off. Let's look at the net force in the x direction for this force diagram. It's going to be the x component of the force of gravity, which is mg sine of theta, but sine theta is just 0.6 L over L, which is 0.6 sine of theta, and then plus the force of friction is 0.4 mg. That's equal to ma. So obviously this is equal to just mg, so a is equal to g actually when it's going up the incline. Okay, now let's look at it for going down the incline. When it's going down the incline, I'll just redraw it right here. Actually, I'll tilt the reference frame this time. So, I mean, for when I was calculating going up the incline, I was also tilting the reference frame, but I didn't explicitly write it down. I'll just explicitly write it down right now. So this is going down. So this is the normal force, and this is force of friction, and this is the force of gravity. This is theta. So the force of gravity in the y component is still the same, 0.8 mg. This is still 0.8 mg, and this is still 0.4 mg. And this x component right here is still sine of theta, which is 0.6 mg, right? But now the force of friction is opposing this, so delta F in the x direction is going to be 0.6 mg minus 0.2 mg. And that's equal to ma. So now we see that, sorry, this is 0.4 mg. I was getting a bit ahead of myself right there. This is 0.2 g is equal to a. Now let's plug in, so wait, hold on, just add in the correct subscripts. This is a up and this is a down. So now let's plug in a up and a down to this equation. So a up is g, tu squared is equal to a down, which is 0.2 g, times td squared. So g's cancel out. And then we want the time td in terms of tu, so let's isolate td. So multiply, so this is just 1/5, right? 0.2 is just 1/5, so let me cross that out. So we multiply by 5 on both sides, so td squared is equal to tu squared times 5. So that means td, take the square root of both sides, square root 5 tu. And that gives us this as the answer. You could have also kept it in this equation, and you could have solved it this way, but the only thing, you wouldn't be able to solve it with only just these two equations. You would also have to say 0 is equal to a up, t up, so negative a up, t up, right, plus v naught, right? We have to also use this kinematic equation to get v naught in terms of a and t. So it's still possible to do it this way, but this by just thinking about it like this makes it a lot easier.